flying boat. It was intended for the growing transatlantic market.
They were developing a docking system. In fact, that was in use at Southampton, so you no longer were taken out to your flying boat in motorboats. You'd walked aboard it from docks, and there would have been docks at either end, drive the aeroplane in, tie it up, and then walk ashore.
The Princess was one of the largest aircraft ever built.
Well, it was a double-decker, so we had upper and lower decks. We had provision for cocktail bars and all the rest of it, and double-berth cabins. It was definitely going to be an upmarket luxury way of crossing the Atlantic in about 7.5 hours.
An atom-powered flying boat might have other uses. Atomic power was also being developed for a new generation of submarines that could lurk for months under the sea. New flying boats with atomic engines would have the range to hunt them down. September 1949. A lone US B-29 reconnaissance bomber picks up samples of radioactive material high above the Soviet Union. Russia had joined the nuclear club. The next year, North Korea invaded South Korea. The Cold War had turned hot. These events were to accelerate the plan for an American atom-powered bomber.
The Congressional Joint Committee on Atomic Energy was very much in favor of going ahead with promoting and going ahead with the nuclear bomber. The Atomic Energy Commission itself also was. They developed eventually a special subdivision which did that work. And within the Department of Defense, the Department of the Air Force, there were a lot of great hopes for the nuclear airplane.
In 1951, the Atomic Energy Commission ordered into production the world's first experimental nuclear-powered aircraft.
The designated aim, as stated in 1951, was to produce 2 flying test beds, so 2 flying nuclear-powered aircraft by 1957. And the program started with a series of testing the shielding requirements for the crew.
The major issue was how to protect the pilot and crew from the effects of radiation coming from the reactor. One solution that was seriously canvassed was only using older crew to fly the aircraft. The theory being that they would be irradiated to some degree anyway, but if they were beyond child-rearing age, then it wouldn't matter so much.
You had to use all these tricks, like base it on uninhabited islands and things like that. Use old men for the pilots so that the effect of radiation on the gene, on the sperm would not get into children. They were going to have pilots, they called them the NEPA man.
To gain experience in dealing with radiation shielding, it was decided to build a flying reactor before the atomic engines were ready.
Well, they were talking about special aircraft because nobody knew how much it was going to weigh, but it looked like it was going to weigh an awful lot.
So the US Air Force turned to its biggest aircraft, the mighty Convair B-36 bomber. The B-36 was the largest American bomber ever built. It had a wingspan of 70 meters and a range of 13,000 kilometers. At first, the B-36 was powered by 6 conventional propeller engines, but later versions saw the addition of 4 jet engines for greater speed and load carrying, giving rise to the phrase 6 turning, 4 burning. Aircrew called it the aluminium overcoat.
The B-36 for the first time gave the American Air Force the capacity of what we now call global reach, global power. That is, that you can reach anywhere in the world with a bomber and influence events there through bombing them.
In 1953, an ordinary B-36 bomber was selected as a testbed for the atomic bomber program. It was modified to carry a small reactor in the aft bomb bay. The reactor was not connected to the engines. A new nose section housed a 12-ton lead and rubber shielded compartment for the crew of 5, pilot, co-pilot, flight engineer, and 2 nuclear engineers. There were also water jackets in the fuselage and behind the crew compartment to absorb radiation from the reactor.
After conversion, the aircraft was redesignated the NB-36, the N standing for nuclear. What they did was they took an actual working nuclear reactor and they put it in the aft bomb bay and they flew with it. And the point being, could you protect the crew from the radiation from a working reactor?
The whole essence of this experiment was simply to test whether you could fly a nuclear reactor in an aircraft and not kill the crew through radiation while doing it.
If you couldn't solve that problem, then it didn't matter whether you could make the engines work. No one would fly it.
The first flight of the NB-36 with its atomic reactor was on September the 17th, 1955. The pilots christened their aircraft the Crusader. The tests proved that the radiation could be contained, provided there was heavy shielding. Atomic-powered flight was a step closer. But now, another problem had to be resolved. It was all very well flying with a reactor, but what happened if you crashed? Because of this danger, the Air Force took very special precautions. Flying beside the NB-36 on every mission was an Air Force transport plane carrying a platoon of Marines.
The plan was that if ever the NB-36 crashed, the Marines in the accompanying aircraft would instantly parachute out, seal off the crash site from prying eyes, obviously to protect any nosy civilians. That could have been quite dangerous, and the Marines being the Marines, they nicknamed this unit the Glow-in-the-Dark Brigade.
Between 1955 and 1957, the NB-36 made 47 successful flights.
The problem now was to get an actual working aircraft into the air. And the division of labour was that the Air Force would provide the airframe and the Atomic Energy Commission would provide the working engine.
The planned propulsion system would weigh 80 tons. The whole nuclear engine unit, including the reactor, was to be built as a single module and removable for refueling and repair. The challenge now was to get an atom-powered engine to work in flight. An ordinary jet engine works by sucking in air through an intake and compressing it. This means that more of the oxygen required to burn the fuel is squeezed into the combustion chamber. The aviation fuel then burns with the oxygen, causing continuous rapid heating of the air. This heated air expands rapidly, creating thrust to propel the aircraft forward. A jet engine can attain great speed. However, there is a drawback. A fast jet engine is fuel hungry, yet the aircraft can carry only so much aviation fuel. That is why modern military jets are so dependent on in-flight refueling. But an atomic motor would solve this problem. The fuel-oxygen combustion process is replaced with the heat from the reactor, which lasts for months or years at a time.
The theory of an atomic engine is very simple. In fact, it's simpler than a jet engine. You simply take the air and you put it into the reactor, which suddenly heats it up. It's not even a chemical reaction. The air just expands, pops out the other end, and pushes the plane forward.
The theory was simple, but the engineering was not. The scientists at the Atomic Energy Commission came up with two competing ways to build an atomic jet engine.
There were two main approaches to nuclear aircraft propulsion. One of them involved reactors that simply had longitudinal holes, and the air came in one end cold, passed through fine holes inside the reactor, became very strongly heated, and produced thrust coming out the other end. Well, the advantage of direct power is that it's simpler. There are almost no moving parts. The air goes into the reactor, passes through a lot of little holes through the reactor, comes out hot. So in principle, it's simpler.
But this so-called direct cycle engine proved to have a major drawback.